more foolproof, we're going to hit record and move this thing out of the way. Okay, now we're in business. Announcements. So I sent out an email about this, but just in case as a reminder, I have now finished recording videos for everything. So your very first homework is now available. So you did homework 0 as a practice to get acquainted with the homework system. Homework 1 is available and due next week. To help you with that, I have a handout and then 4 different videos to get started with the virtual desktop if you plan to use SAS or Stata, and then how to actually use SAS, how to use Stata, and then how to use R. So if you're planning on learning R, I would not actually go through the virtual desktop. You can, but it runs really, really slow. The whole reason that people try to learn R is so that they can use the software on their own machine. So that is what I would recommend that you do. You can install R regardless of your operating system, Mac, Windows, Linux, what have you. So those videos should help you. At the end of each of the videos for the programs, SAS, Stata, and R, I describe how you would use the example files that I give you to get started with your homework. So inside the homework portal, when you log into homework 1, there will be 4 links at the top. One of those is going to be the data set that you're going to use to complete the homework. The next 3 are what I call starter syntax files, where it's just a little piece of code that you can paste into your program that will help you import the data, apply the variable labels so that you know what you're working with. So those resources are available. It looks like most of you have done homework 0 so far. How did that go? Good? Any questions on how to do homework or use the system? No? I'm told that people like it. Like if you have to do homework in stats, it's good to get feedback immediately. So the tricky part for the first real homework is not going to be what I'm asking you to do. I'm asking you to have the computer spit out things like means, frequencies, stuff like that. The tricky part is going to be communicating with it to understand where your files are. That is the hardest part. So if you find yourself trying to communicate with the programs and your data aren't being imported and you can't figure out why, ask for help. So I'm happy to meet with you during office hours and we can do screen share so I can see what it looks like on your end. If office hours don't work for you, we've got office hours for 3 different TAs. If those still don't work for you, shoot me an email and I'm happy to Zoom with you individually. That way you can show me what you're working with and I can try to help you figure out what's going wrong. Okay? All right, so we got nods and thumbs in the classroom. Zoomers, we good? All right, rock and roll. Any questions about anything before we dive back into the stuff we've been talking about? Everyone's really quiet. Well, to be fair, it is 2:08 on a Tuesday, which sort of lends itself to, this is the slumpy part of the day. So thank you for being here. If you look a little slumpy, that's fine with me. I can feel that. I appreciate the attendance. But we are heading back to what we were talking about last time. Okay, I am screen sharing, right, Zoomers? I'm always paranoid that I forget. One thing I'm not doing, though, is the transcript. Let me fix that. Let's see if I can add that. I may not be able to do it while I'm sharing. Let me stop the share temporarily so that I can turn the transcript on, because that button, for whatever reason, is not on my thing. And now I'm promptly going to hide it from myself so it doesn't distract me. And reshare. There we go. Okay. So this is what we were looking at last time. We started talking about general linear models. So general linear models, generically speaking, are for predicting quantitative outcomes. The simplest model that we would have to start with is what we were talking about, introducing new terminology. The idea of an empty model, this thing right here. Empty model means no predictors. So it's not really a model in the sense of making a prediction that is useful. The reason that I teach it is because it's a baseline for establishing how well subsequent models perform. That's what its purpose is. So it's more of a pedagogical tool than a something that you would need to know, because all it does is spit back the sample mean and the sample variance. Then we started talking about what else is going to be spit out, and the idea of quantifying uncertainty. Move that out of the way. So we started talking about the difference between standard deviation and standard error as two ideas. And each of those things sounds very similar to each other. They're both like standard something, and error and deviation both have the same kind of offness vibe to them, but they refer to different levels of analysis. So if I'm talking about a standard deviation, for instance, this is slide 11, I'm talking about the spread of a variable across the participants in my sample. So this example picture is a histogram for income in thousands of dollars. On average, the sample average is 17.3, so $17,000 on average. But clearly, just from the picture, we can see that that number doesn't describe everybody. It's what happens on average. The standard deviation tells us how far off on average any one person's outcome is from the mean. So in this case, we have 13.8. On average, people are off by $13,000 from that mean of 17. So that's one thing. So if I have variance computed, I take the standard deviation, the square root of that is standard deviation. Now the new thing, a different question. How good of an estimate of my mean for the population is this 17? If I were to redo my study, like the replication crisis, right? That's a whole thing. People are concerned about how replicable results are. That's what I'm talking about. If I were to redo this same study, would I get 17 as my mean again? Probably not. But how far off would it be? In other words, is it 17 is the mean, and that mean is a good estimate of what the mean income is in the population that I really want to talk about, but I don't actually have? Or is it like, yeah, it's 17, but it could be anything? So where you see this in the real world is in poll results during election years, right? You might hear that, Biden is ahead of Trump by 8 points, or Trump is ahead of Biden by 8 points, but what's the next thing the broadcaster should say to contextualize that number? Yeah, margin of error, right? If Trump is ahead of Biden by 8 points in this poll with a margin of error of 10 points, then that 8 points is basically worthless. It's well within expected fluctuation as measured in that sample of people. If the margin of error is 2 points, okay, yeah, well, 8 is a lot then. So it's a way to contextualize what this information is telling us with respect to how consistent we would predict this result to be across similar samples. Standard error is trying to tell us that. Yes, question?
I don't understand the marginal error part.
The margin of error is I think a layperson way of getting at the same idea. When people on the news report results of political polls as to who is ahead in a given race, they often report by how many points a given candidate is ahead, but then they also tell you the margin of error to the poll. And that margin of error contextualizes how big of a lead any candidate actually really has. So think of it this way. If I step on my bathroom scale after a week of eating lettuce and turkey and nothing fun, and I lose 5 pounds, yay me, right? Assuming that's what I was trying to do. But if my scale has a margin of error of 6 pounds, did I really lose 5 pounds? Or would I hop back on and get a completely different number? So when we're measuring things that are not as easy to measure, like height and weight and things that are like definite, how good of a number it is a really important part of trying to interpret the results. It's not just about the number you get. How good of a number is it? And the very first number that we've talked about is a mean. So now we're talking about a standard error for the mean. But the same idea applies to every single result that you can get out of an analysis. Every number that comes back is going to have an uncertainty to it that we have to take into account. Okay, how are we doing so far? Okay so far? All right, cool. Let's see then. So let's go with slide 11 again, because we can go back over this stuff. So picking up where we left off then. So the mean is 17.3 in this data set. How good of a mean is it? If I redo the study in the same way, same sample size and all that stuff, would I get 17 again as my sample average for this variable? Not exactly, but how inconsistent would it be across repeated samples? In order to know that, we have to find some way of capturing what we expect that estimate's sampling distribution to be. Meaning, across repeated samples, how inconsistent is my result expected to be from any one sample? And there's two things that go into the standard error for a mean in particular, and they also go into standard errors for other things as well. So to demonstrate this idea, I made up data. I got 100,000 fake people, fix my typo from last time, in this fake data set that I have complete control over, because fake people are very well behaved when it comes to participating in research. They answer all the questions. They come back at every occasion. If you make up the data, it's beautiful. Fake people are well behaved. This data has been created to have a mean of 10. I know that. It was created to have a variance of 25. I know that. It worked. That's what this picture is showing, with the red and blue lines overlapping. So on average, within this data set of 100,000 fake people, any one person is predicted to be off from this mean by 5 on average. That's the standard deviation of this variable within this population. Okay, with me so far?
Was there a reason why you chose those numbers?
Nope, none at all. The reason I chose those numbers is because those are the numbers that I want to see come back. That's it. And I made a normal distribution because that's one that you probably has seen before, but I have another demonstration of this using a not normal distribution in a couple slides. So yeah, these are completely arbitrary. So what I did then is go into my fake data set of 100,000 fake people and grab out samples of different sizes. So I went in and told it, get me 5 people, calculate a mean. Get me another 5 people, calculate a mean. Get me another 5 people, calculate a mean. Did that 1,000 times. Then I said, okay, get me 10 people, calculate a mean. Another 10, calculate a mean. Over and over again for 6 different sample sizes. And what these histograms are showing is the sampling distribution of the mean across those repeated draws. So if I only have 5 people in each sample, what I get back as the mean of those 5 people is really anyone's guess. It's all over the place. The right answer is 10. That's this line right here. But any one sample of 5 people, the mean could be anywhere from 5 to 15. So if you don't have a lot of people, what you get back is expected to be very noisy. You don't have a lot of confidence in the results if you don't have a lot of people. That makes sense at an intuitive level. The more people that you put in any one sample, so 10, 15, 20, 30, 50, the more consistent those guesses for what the mean should be become. If I have 50 people, now I'm pretty close to the right answer of 10 most of the time. I'm really only off by like 8 to 12 around the correct answer of 10, whereas with 5 people, I'm off from like 5 to 15. So these pictures are demonstrating a sampling distribution, how that result is expected to behave across repeated samples of the same kind. And now I just felt my caffeine kick in. I'm going to pause for a second and take a drink and ask for questions. Gotta love it. I just learned recently that Mountain Dew has started getting into the hard Mountain Dew. There's like a new alcoholic Mountain Dew. I can't imagine how that would taste, but I bet it's awesome. I promise you though, this is just standard diet Mountain Dew. There's nothing, no funny business happening in the Lindquist Center. Not today anyway. It's not that kind of lecture. I have been known to teach on my birthday after going out to lunch and having a margarita, though. That has happened in the past. I'm not going to lie to you. but not today. It's not my birthday. Anywho, sampling distribution, that's what these things represent. And if I made up the data, I have the power to draw as many samples of the same kind as I want to actually see this happen.
I
Yes?
have a question. So there's 50 people on the bottom right.
Yep.
If you were to have 1,000 people, would it still, at what point would it like reach its peak and it would look like that bottom right? Or like, so if I had 1,000 people, would it look more similar to that bottom right sample?
So the question is, if I had 1,000 people, so if I kept this experiment going and added people, it will keep shrinking and shrinking and shrinking until it's basically like one line where you get the right answer every time.
Okay.
So yeah, you can think of that as an asymptotic result. If you hear that word, that means if I had everybody in the world, like what would eventually happen. But yeah, you're exactly right. The more people you have, the less variable your result would be in any one sample. It may not be 10 exactly, but it might be like 9.5 to 10.5, as opposed to 8 to 12, as opposed to 5 to 15.
Okay.
It tightens.
And so, is there any negative, like, I'm brainstorming negative things that could come out of having too big of a sample, but from this, it's not negative if we're just talking about the mean. Like, you want a lot of people.
Yeah, you want more.
But-
the answer is always more, as to how many people you want.
As far as interpreting it, the negative, the drawbacks could be people get lost. Like, individual, like, people's answers get lost.
I would say that people's individual answers getting lost is not what this is about.
Okay.
So the question was like, would you ever want to have fewer people? And the answer is no.
Okay.
So the idea of power analysis, are these words you've heard before, statistical power, that's one thing that and when you're planning research, you're supposed to think about is how many people do I need to do this study? That's kind of what we're talking about. Like, how many people do you need to get a good answer that you can trust? Like, if you think something should be 10, if you only have 5 people, you're not going to get 10 back. Like, you're going to get anything, basically. And the tighter it gets, you have more people. So we're talking about how reliable or replicable a given result is from one sample. The more people you have, the closer it is to what it's supposed to be. And one second, I had a question on Zoom and then we'll get to yours. So with different sample sizes, does the standard deviation change or is it the standard error that is changing? Oh, great question. The answer, all of these pictures were made using a standard deviation of 5. What is changing is the standard error. Yeah.
Thank you.
Yeah. So, like, on average, each person is off from the rest of the people in their little sample by 5. That is true in all of these pictures. What is changing is how far off any one sample's answer is from what it's supposed to be. More people, more right.
I think I meant to ask that question, so whoever asked that, that was great.
Yes. Okay, question in the back. Can you say it loudly so we can hear you?
Yes. Besides the size of the sample, you said you're increasing them. What about the number of the samples?
So the question was, besides the sample size, so we're talking about whether I grab 5 people, grab 10 people, or grab 15, does it matter how many samples? And not really. These histograms would look a little wonky if I had fewer draws. The 1,000 was used just to kind of fill in the gaps to make a nice clean shape, but no, that doesn't matter. Okay, so yeah, everybody in any one of these samples is expected to be off from the sample's mean by 5. What is happening is that how good that mean is relative to the population mean it's supposed to be, that's what's getting better. The standard error is what's getting better. So at the risk of confusing you, let me say this. The spread of these sample results, what the standard error is supposed to be getting at is the standard deviation of these results. I know that's like, what? It's one of those things that is like, it's hard to picture at first. But standard error is referring to the behavior of a result across repeated trials. Standard deviation is referring to the behavior of a person within a sample. So if I were to calculate how far off on average each of these results is from the right answer, the standard deviation that I come up with, that's my standard error. A standard error is a standard deviation of a sampling distribution. That's what it's supposed to be getting at. So for those of you who are on Zoom, I see pencils poised like, no. And I see a lot of faces that are looking like that. We got questions. So in the sample of 50, it doesn't look like any of them are off by 5. Yeah, no, because that's what these pictures are not showing that. You can't tell from this picture how far off any one person is because these aren't people. These are samples. So we're at a higher level of abstraction where the people have left the building. This is the summary of the people and how that summary changes across repeated samples of the same kind. The behavior of that summary, the mean, is what the standard error is supposed to be capturing. Okay, one comment that makes sense. So this is a summary across samples that we're looking at here. And you're absolutely right, the more people, the more right you get, the tighter it gets. Eventually would collapse onto just like very little variability. All right, okay-ish. I'll go with okay-ish. Okay-ish. Yeah, it's fine. If this isn't like absolutely crystal clear yet, that's correct. It's not supposed to be. This is the first time you're hearing about this, or you heard about it in a different way. Because guess what, folks? We don't normally have this. The only reason I could even make these pictures is because I made up data with which to make them. In reality, when we do research, we have one sample that we're working with, maybe 2, but that's it. But nevertheless, even though we only have one sample, we still have to find a way to think about how inconsistent that sample's results would be across other samples of the same kind. That's what we're trying to get to. So one thing that factors into how inconsistent a result would be across samples is sample size. And so this is a table that summarizes what's happening in each of these pictures. So the mean is pretty close to 10 on average. This is the mean of the means. That's what this column represents right here.
The means of all the individual samples put together.
Yep.
Okay.
Yep, this column right here is so it's Y with an S for each sample. This is the mean of all the sample means. On average, it got it right. But what would have happened in any one sample is not right. So if I only have 5 people, the standard deviation of these samples is such that the sample mean is expected to be off by about 2 in any one set of 5 people. If I got 10 people, the sample mean is expected to be off by 1.6 for any set of 10 people. And if I have 15 people, it's only off by 1.3, and so on and so forth. Question?
Is it bad to look at that by saying like, okay, so the sample size of 5, the margin of error is like greater than 20%. Is that an incorrect way to look at that?
So the question was, can I say that the margin of error if I have a sample size of 5 is 20%? Given these values, you can say that.
Okay, and then obviously then you can like look down and
Mm-hmm.
it's more accurate.
Yeah, but it's relative to what it's supposed to be.
Right.
Yeah. So given that the mean is 10, a nice, like, easy number to work with, yes, you can think of it that way. Yep. So the standard error of the mean that we're going to end up with is supposed to be this column. Standard error of the mean tells you how far off on average any one sample's mean is from what it's supposed to be. It's the standard deviation of the sampling distribution of the means. Not the people, the samples. Standard deviation is about the people. So in this picture, for all of these cells, any one person within each of these little samples is off by 5. But if I take my sample mean, that mean is off from the right answer, the population mean, by 2 or 1.6 or 1.3 or 1, depending on how many people are in my sample. Okay, a little better? What's a little more than ish? I don't know, I need some new vocabulary.
Ish squared.
Ish squared. Nice, I like the stats humor. So when we asked my son how school was, you know, those of you with children might, yeah, they don't want to answer that question, right? Fine, or he just grunts while he shovels food in his face. And so we go with thumbs. We got thumbs sideways just means okay, thumbs up means good, and then thumbs down means bad. And he'll do like 45-degree angle, like, you know, like somewhere between, you know, okay and bad. So if we go with thumbs, like this would be ish. Just crank it up a little bit to ish squared. Hopefully that's where we're heading towards. Heading to the top, but we're not there yet. Okay. So what if I mess with this? So intuitively, let's think about this. What if people within a sample were closer together? What if I took this standard deviation that I made the fake data up, I can do whatever I want. What if I tweak this down to 3? So within any one sample, people are closer together, they're less dispersed. What do you think is going to happen to this picture? Yep, this is the correct answer, squishing. Yep, same thing. Because if people are less spread out to begin with, then it's a lot easier to find the mean. If you start with a football field of variability, where the middle is anyone's guess. If you start with, you know, a yard of variability, the middle is much easier to find. So lo and behold, let's do that experiment. Standard deviation of 3 instead. New fake set of people, okay? Here's what the pictures look like. Now if we look at the same standard deviation, now if I have 5 people, but any one sample, people are off from each other by 3 on average instead of 5, now the mean is off from the population mean by 1.4 on average. This used to be 2. And if I put those two next to each other so you can compare, the top row on slide 17, this is standard deviation of 3. So any one sample, somebody's off from the mean by 3 on average. Bottom row is standard deviation of 5, off from the mean by 5 on average for people. Same sample size of 5, 10, and 15, you can see what happens. So the more people you have, the more consistent your results are going to be across repeated samples. The smaller your margin of error. But also, the more consistent your people are to each other. The mean is a better descriptor of individual variability. It's easier to find. So if I put those two ideas together, then people way smarter than me figured this out a very long time ago. For any one data set, even though I don't know what the right answer is supposed to be, and even though I don't have repeated samples, I can still guess as to what the standard error is going to be. And it works. So this is the formula for what you may have learned as the standard error of the mean. And the 2 factors that go into it are exactly what we just discussed. The numerator, this little thingy here, this is sigma. What's that? Feel free to read from the slide. Yeah, population standard deviation. And n, what's big N? Sample size within a sample. So the more spread out people are from each other in a sample, the bigger the standard error is. The more people you have, the smaller the standard error is. And in practice, we don't know what sigma is. Sigma is an idea. It's the right answer for what the standard deviation is in the population. We don't know that unless you make up the data. So in practice, we use the sample version instead. And that substitution matters more if you have less people, fewer people. Okay. So then words. I warned you my slides have a lot of words, right? That's so you don't have to write this down. So putting it back onto our example then. Standard deviation versus standard error. So the mean of my example data, 17.3. Cool. I calculate how far off each person is from that mean, each person's residual. So y is their income, what they actually got. Beta 0 from my empty model is the mean. So how far off you are from the mean is E. If I take those E's and square them, add them up, divide by n minus 1, that's my variance. Take my variance, square root that, I got my standard deviation. So in this picture, these are people. In this picture, the average income is 17.3, but any one person is predicted to be off from that average by 13.8 on average. Question?
And this would be what you call the data set, not a
Yes.
sample. Okay, that's a
Yep.
data set, and then a sample is the data sets all put together.
A sample is one data set.
So then what are the individual steps?
Rows.
Rows?
Rows.
Okay.
Yep, these are actually real data. This
Okay.
is from the General Social Survey of 2012. So it was a data set that came with one of the textbooks that I used in a different class, and I stole it and did stuff with it. So yeah, in a given data set, a column is a variable, and a row is a person, in most cases. Generally speaking, a row is the smallest level of measurement. So if person is the smallest, it'd be a row. If you measure people multiple times, an occasion for each person would be a row. But the term sample and the term data set are interchangeable.
Okay.
One set of people by which to get results from. Okay. So these are people, what I got right here so far. Now the next question is, if I redid this study with new real people, would I get 17 back? No. How far off am I going to be? Well, that's my friend's standard error. So if I plug in my estimate of my standard deviation divided by n, or you may see it this way, either one, that number shows up to be 0.5. So what that number is telling me then is for another sample, how far off from the right answer population mean is my sample mean going to be if I have 734 people and a standard deviation of 13.8? The answer is 0.5. So any repeated sample is expected to have a mean that's off from 17 by 0.5 on average. That's pretty tight, right? So like plus or minus 0.5 would get you to pretty much the right answer, because this is a lot of people.
And that's because the survey used so many people.
Yeah, and this is actually a subset of a subset that I selected for various reasons, but the original survey has thousands of people. Mm-hmm. Okay, how are we doing, thumbs? We got somewhere between sideways and up. Zoomers, you want to participate in my poll? Yeah, Zoom polls, take that. We got a thumb poll happening right here. So on average, I would say we're somewhere between ish and good. And how far off on average? I don't know. We're out of units here. Whatever the square root of ish is. Okay. So then showing that it works. So here's the same fake data that I showed you just a minute ago. Standard deviation of how far off any one sample's mean is from the population mean. If I have standard deviation of, this one's 5, so the original sample, it was 2 something. If I calculated on average what the mean standard error is for each of these replicated samples, it comes up pretty close. So let me back up. This column right here in bold, that's what actually happened, because I made the data and I know. So any one sample of 5 people, the mean of that sample of 5 is off on average from the population mean of 10 by 2.1. That is what happened. These 2 columns over here are predictions of what could have happened using our new handy-dandy formula for the standard error of the mean. And it works. It works better the more people you get. So with 5, it's a little bit off. For 50, it's pretty darn close. So every result that you get out of a model is going to have an estimate. The next column over is going to be the standard error for that estimate. How far off on average would you expect that result to be across repeated samples of the same kind? Both of those pieces of information are important. Okay. Questions? Yes?
The greater the n then,
Yes.
it also then looks like the more tight that the sigma and the
Yeah, the greater the n, the tighter the sampling distribution. The tighter what the result could be in any one sample is. The variability across repeated samples is the sampling distribution, and the more people, the tighter that thing gets. And then the more variability you have within a sample, the wider it gets. If people are more different from each other to start with, then what the sample mean is going to be is more different across samples. Okay. All right, Zoomers, questions? Got a whole lot of black boxes here and a few faces. We're good? All right, let's keep rocking and rolling. Yeah, so this works. And so this might be the point where you'd be like, yeah, Lisa, but didn't you cheat? Because when you made up these fake people, you made them out of a distribution that looked normal. So is it, I mean, you just got the same thing back again, didn't you? No, I didn't. I didn't cheat. Turns out this works, no matter what your data look like to begin with. So I made up new fake people. This distribution, this shape, where I have a boundary on the left-hand side and it kind of trails off here. This is positively skewed. This is a count distribution. The number of events that something happens, where the lowest you can have is 0 and the highest you can have is positive infinity. By the way, I used what's called a Poisson distribution to generate these data. So this is a statistical function that gave me this result. Where you would see a distribution that looks like this in practice. So let's say that this depicts the number of times that I have to tell my son Hugh to do something before it actually happens. On average, twice. I know, he's pretty good. Unless he's watching Zach Scott play YouTube videos, in which case he cannot hear me whatsoever. I have to manually walk over and press pause on the iPad and then take it away and be like, it's time for dinner, or whatever we're doing. Eating is the worst. He hates to eat. He doesn't understand that he's starving until he sits down and starts shoveling, but I digress. So this is a count of events. On average, it takes me 2 reminders to get him to do something. It could be 0 on a good day, could be 7 on a bad day, right? This is a count variable. So this is positively skewed. It's made up of integers, right? You can only have 0 times, 1 time, 2 times, 3 times. Does this distribution look normal to you guys? Does it look symmetric and continuous? No, it's not. But guess what? By the way, in this distribution, the mean and the variance are the same number. That's just one of the perks of this. But guess what? It still works. So from this count distribution of fake people, same typo, GR.
That's still people.
Still people. Now these are samples.
This is the sample of the error.
Yep. So I grabbed 5 people, got a mean. 10 people, got a mean. 15 people, got a mean. Did that 1,000 times at each of these sample sizes, and lo and behold, I get the same shape.
And the other one was just one person.
This is one set of people, although my example was longitudinal, so multiple observations for one person, but it'd be one data set.
It could be either way.
It could be either. This could be a count for individuals in a sample, or it could be a count for occasions within an individual. Like if this were an N of 1 design, and I was studying my son, then this could be his distribution across time. But these are not people. These are samples. But the same thing works. It's a little messier with lower people, fewer people, but it's the same thing happens. The more people, the tighter it gets. And if I look at the actual standard deviation as to what happened. So if I have 5 people, on average, the mean is off by 0.6 in this picture right here. The standard error that was computed using that formula is also 0.6. So this column, standard deviation, is what really happened, and the only way I know that is because I made up the data and I could do the repeated sampling. This column on the right is the standard error that is predicted from that formula. It works. So this standard error is going to show up next to everything we care about. This is where it came from. It's the idea of what should happen across repeated samples of the same kind. How inconsistent is a given estimate? Result, summary, estimate. All of those words mean the same thing. Okay. By the way, the thing that I just showed you, that this works even if you have a count distribution, that's called the central limit theorem. That might be something that someone made you memorize at some point. Does that sound familiar? Central limit theorem. No? Okay, well, if it's a Jeopardy question, now you know the answer. The statistical property that as you get a bigger sample size, the sampling distribution of your mean becomes normal. What is central limit theorem for 500? Actually, that'd be the bottom one. That'd be like 1,000 maybe. But anyway, it's one of those things I mentioned because it's a common misconception that people think that the more people you get, that means that your sample is going to have a normal distribution. That's not true. It's the sampling distribution of the mean that gets more normal. So that's what this means. Why this matters for us is that no matter if we have a count variable to start with or some other kind, when we get to talking about what we can say about our results, we're going to borrow this shape because we know that the results are going to take this shape. Because a given question would be then for any one sample, how far off is it away from what it's supposed to be? Is it too far? Is it with an expected fluctuation or is it aberrant? And this shape is going to help us decide whether any given result is expected or way too far out to be reasonable. So like if I'm looking at this picture where the right answer is 2, and I happen to grab a sample of people where the mean is 4, I'm over here. That means that is probably not the same population. 4 is too far away to be believable. So this shape is going to help us decide what results are too far away from what they're supposed to be believable. Okay, it works. All right, questions? Changing gears a little bit in the next slide. So all we've done so far is talk about predicting an outcome from an empty model, which is our baseline for starting. It's a crappy model, but it's what we judge how much better we can do by adding information to it. And where results are going to be 3 pieces of information. We're going to end up with a mean. We're going to end up with a variance around the mean that talks about our people. And we're going to end up with a standard error that talks about how good of an estimate that mean is. How wiggly that mean would be across samples. We're going to get those 3 pieces of information back.
And the only time the standard error would be 0 would be if you had the entire population. Somehow.
I would say that by the formula, it would only be 0 if everybody had the exact same value in the population. So like if the standard deviation were 0 and everybody had the exact same, then the mean for every single sample would be the exact same number. Otherwise, it's going to be like, not exactly the same, but it gets closer and closer and closer. Yeah, like off in the 3rd decimal place, close, once you get thousands of people. Yep. Okay, so let's add information. Welcome to your very first general linear model with a predictor. If you were reading about this in a classic introductory textbook, the title of this chapter would be called Simple Linear Regression. Why simple? Because they're trying to piss you off. That's my cynical answer, but that means in this context, there's only one predictor variable, this x. Why linear? Because what we're going to do is make an equation for a line. So if anyone's looking at this and going, hey, is this like algebra? Yes. Yes, it is. You learned this many moons ago as y equals mx plus b. Different letters, same idea. This is an equation for a line. So we have included now another piece of information that's x here. So this is a generic representation. What I am saying is that y is going to be predicted by this other information. So what do you think might predict someone's income? Let's go with education level. That's why we're all here, right? Why in general people would pursue higher education. One of those goals eventually would be to have more income potential, sure. So in this generic equation, I'm giving you definitions that hold regardless of what x and y happen to be. So this thing right here, beta 0, this is my fixed intercept. Its definition is this is what y is predicted to be if x is 0. Because that's the point where this new piece right here would drop out and you'd be left with just beta 0 and e. Beta 0 is your intercept. It's sometimes called the constant, which is a terrible name. I'm going to go with intercept. This would be the B part of the algebra analog. So previously, beta 0 was the sample mean. Now that we have this piece in here, it's not the sample mean anymore. It's the mean that's predicted specifically at x equals 0. So beta 0 is like your jumping off point. Okay, what's y going to be? And then how is y predicted to change as we move up on this x variable? So beta 0 is kind of like a baseline for a prediction. It's known as a conditional mean or expected outcome. And all it does is adjust for mean differences between x and y. So you can figure out, like mathematically, what it's supposed to be just based on that information. The slope is beta 1. So that's the m part of the algebra analog. And every slope in the history of the world, no matter if you take one stats class or 10, a slope is a slope is a slope has the same definition. It is the change in y for a 1 unit change in x. Now I say difference because I'm talking about a cross-sectional application of this, and change kind of implies that people can change their values, which isn't true if you only have one data set. So the difference in y for a 1 unit difference in x, that is what a slope means. To make your life easier, commit that one to memory. Just memorize it. Have it at the top of your head. That is what a slope tells you. So if beta 1, my fixed slope, were 3, that means that for every unit more of x as my predictor, y goes up by 3. If beta 1 were 0.3, then for every unit more of x, y goes up by 0.3. It's always talking about the change in y. That is what the number means, per unit. Now, unit is a terrible word. It's a statistics word. It is not an interpretational word. Units would be years, inches, pounds, dollars. What makes one value of x different from each other? Instances. Number of correct responses. Like for every additional response you get correct on x, this happens to y. See, that's a throwback to your other class. We got some folks taking measurement classes. We're going to try and tie those together. Yes, question?
So it's like for every 9 months, say, of advanced education, your income could go up a certain amount.
Yeah. So
9 months would be 1 unit or 9 units?
That's up to you.
Okay.
Yeah, so there was a question. So if a unit was 9 months of education, like an academic year or something, you could scale it that way if you want. So for every additional 9 months of schooling you complete, this happens to your outcome. That this happens, That's your slope. It's up to you. So if I were doing a research study about cognitive aging and I were working with older adults, and my sample of adults range from, say, a 50-year-old up to a 100-year-old, I might say per decade of age, this is what's predicted to happen to you. If I'm working with newborns and I'm following them for every additional week they're alive, this is what's supposed to happen. So it's up to you what a unit is. It's always contextual. And yes, you absolutely have to know what the unit is to understand if this is a lot. Because change per year and change per decade necessarily cannot be the same thing. Okay, so we have no new quotes, it looks like, from the chat window. Zoomers, are we doing okay? Excellent. In-personers would be, I guess, the analog, but that's not really a thing. So one of the things that I am going to do from the get-go in this class that other places, teachers, and books is not going to is talk to you about centering. 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 Yep, this word right here in bold. That is going to mean rescaling my x so that 0 is a meaningful value. That is what it's going to mean. Now, why would I do that? Here's a real-life example. This is core Terminal B of a very populous airport. The picture's a little bit old, but it's from when I used to be in Terminal B quite frequently when I was in a long-distance relationship with my now husband. He worked at the University of Georgia, and I worked at the University of Nebraska, and I became very well acquainted with this particular Terminal B. Any guesses as to where this is? Chicago? Nope. This is Atlanta. Yes, University of Georgia gave it away. That's the nearest airport, major airport. But of course, flying out of Nebraska, you have to connect. There is no such thing as a direct flight out of Nebraska. That's just not possible. So if I'm in Terminal B of the ATL and I've got 50 minutes to get myself some lunch and make my connection, generally I go for airport Chinese food because it's consistent. And if I want to look at this directory and find the nearest Manchukuo or Panda Express or whatever they have there, what do I need to know in order to use this map?
The measurement away, or the distance away from.
Distance away, so it looks like it's scaled in gates. But if I'm standing there in the middle of 8,000 of my closest traveler friends, how do I need to know if I need to go left or right?
Need to know where you are.
I got to know where I am. The first thing you look at in a map is the "you are here" star, right? So this map I'm looking at from the perspective of I just got off the escalators and I'm in the middle, right? That you have to know where you are to know where you're going and how to get there, right? So if we think about that idea, I got to know where I am first. In these models, where you are is tied to where 0 is for your predictor. So for instance, if I have a model predicting the same income variable, so this is the variable we had before with the mean of 17, and I put in years of education, that's my x-axis down here. So in this sample, it looks like the lowest years of education that was reported was 2, and the highest is 20. So 20th grade, roughly, where we all are, give or take. The solution that SAS, Stata, or R gives me is this right here. So the new part, beta 1, that's my slope. That is telling me that for every additional unit x, this is the change in y. Okay, let's put that into the story. For every additional unit x is for every additional year of education. What's going to happen? My income is predicted to be higher by 1.82, $1,800. So the slope of this line is positive. This line is what is predicted by the model. People who have more education are predicted to make more money in this sample. Now, what is beta 0? The definition of beta 0, this is your fixed intercept. This is another thing to commit to memory. Beta 0 tells you what y is predicted to be if x is 0. Because that's where this part drops out, and you're left with just this to make your prediction. Beta 0, in this model, tells me that somebody with 0 years of education is predicted to owe $7,000 a year. -7. And I'm seeing a lot of faces that look like, what? Yes, that is correct. What? So this is like trying to figure out where you're going in Terminal B from like outside the airport. Like you're so far away that your point of reference is all messed up. And so what that value actually comes from is where this line crosses the y-axis. It's all the way down here for somebody with 0 years of education. According to this model, somebody with 0 education is expected to make negative $7.89 thousand. Now that's not necessarily wrong, but it's weird. So let's fix it.
I was gonna ask that, like, can you fix that then for
Yep.
the fact that the 0, would that be like a count? Like the 0 is the bottom?
0 is the bottom if you don't fix it. But yeah, we're going to fix it because this is weird. It's not wrong, but it's weird. So a common choice for fixing this might be, well, let's move it over so that 0 is the sample mean. And I can tell you that in this variable, the sample mean years of education happens to be 13.44. Nobody wrote that down. Nobody wrote down, I have 13.44 years of education. That is not a thing. So let's pick a convenient reference point that's in the middle. How about 12 years of education? In U.S. education, that means that they have a high school degree. Let's move it. So this process of rescaling where 0 is, rescaling is centering. You're changing where the center is. So they made a verb out of it.
And you're doing that to stick with reality, right? Like what we can understand as humans to be true.
You're doing that so that all of these numbers are meaningful and useful.
Meaningful and useful.
Yeah.
Okay.
And that sticks with reality is another way of saying the same thing. 0 is not really logically possible for this variable. That would mean somebody who has never been to school. Now that is possible, but not in the sample. We don't have anybody like that. So if we rescale it, if we recenter what 0 means, the way that we do that is to make a new column that is their original years of education minus 12. Now somebody who had a 12 is a 0 on the new scale. And now my reference "you are here" sign is in the middle of my line. So the value that is predicted by this line at 12, which is my new 0, is 14. So now beta 0 makes sense. For somebody with a high school degree in this sample, they are predicted to make $14,000 a year. For every additional year of education, they're predicted to make another $1,800. Follow up this line, and you can see what it would be for 1 year more, 2 year more, 3 year more, 4 year more, and so forth. Questions?
So when you picked, you picked the mean, right? No, wait, what did you do? Just pick the,
I pulled this out of nowhere.
but I mean, when you rescaled and you repicked the 0 at 12,
I picked 12, because 12 means something.
but why was that again? That was,
So if I had picked the mean, that would have been a fine choice, and that is sort of what people do by default. But to me, it's weird, because there's nobody in this variable who actually had the mean score as my model reference point.
right.
Nobody
So
wrote down 13.44. That's not a real value that's possible. And like if you look, like these little dots, this is a scatter plot, they're aligned at all of these integers because nobody has in-between values. So making like a reference "you are here" sign for a value that isn't possible is weird to me.
Okay, so you just made it the closest value possible to what makes sense.
I picked 12 because it's a meaningful value.
Because we have 12 years of school.
Because 12, because in this country, which is where the data come from, 12. If it were a different country with a different system, I might pick a different number.
Okay, so you picked it based off the mean and then what had meaning?
I picked something in the middle and something that had meaning.
Okay, okay.
Beyond that, it doesn't actually matter. I could have picked 16, and then my reference person has a college degree. But then somebody would be like, well, is it 16 or is it 17 nowadays? And I'd be like, okay, fine, it's 12, because I know what 12 is. Okay, let's see. I think we had Zoom question first and then more in the room. Did I lose a data point at 2 years of experience, and is it okay? So in this case, my picture, I lost these people over here. So the scale of this goes from 4 to 20. So yes, these people are okay. They're just out, they're floating out here over in like terminal A. So thank you for the question. Did you have a question?
Yeah. I want to understand if I'm interpreting the X line correctly. Because I see 0, 2, 4, 6, 8.
Mm-hmm.
And then it shows 0 to 12 years. What is that?
So the question was, what does this x-axis represent?
Yeah.
So this is the new variable that I created by subtracting 12 from everybody's education. So in this new centered, rescaled x-axis, 0 is 12 years. So these can be expressed as deviations relative to my new centering point. The 2 means 14. The 4 means 16. The -2 means 10th grade. Mm-hmm. It still means the same thing, and note that the same exact slope characterizes both of these lines. That's not a typo. I have not changed the relationship between education and income. I have rescaled education so that 0 means something, because 0 is what beta 0 is talking about. And there's no wrong way to center, only weird.
Okay.
You can't get this wrong, because it's the equation for a line, no matter what. It's just, what does beta 0 represent? And is it within the scale of your data, or is it clear outside into the range of extrapolation? We have a question, is this the null hypothesis correct? With respect to a slope, most of the time the null hypothesis is 0. Those aren't words that we've introduced yet in this class, but that's coming. Because that's the next question, is like, well, is that a lot? Is $1,800 a year for every year of $1,800 for every additional year of education? Is that good? Well, what do you expect it to be? If you expect it to be 0, well, that's a lot more than 0. But is it like a lot, or just not really a lot? Then we get into hypothesis tests and whether that's significant or not. That's coming downstream. Okay, where are we at? 308. So you can leave this uncentered and have your beta 0 refer to somebody with 0 actual years of education, but I find that very unhelpful. And when you get into more complex models, more of the terms start to depend on where 0 is, and it can cause you to have results that just are crazy. So from the get-go, every predictor that we look at in this class is going to have a 0 point that's meaningful. So if it's a variable where 0 already means something, cool. Like if it's number of times I have to remind my son to put his socks on, 0 means I didn't have to remind him at all. I could leave it that way and talk about the predicted whatever for somebody who doesn't need any reminders. And then my slope would be for every additional reminder, what happens to your outcome? It's just that in this example, somebody who attended 0 years of school didn't happen. So 0 doesn't mean anything as an actual 0. We want to rescale center so that 0 means something, and I did that by subtracting 12. Okay. Residual variance. Okay, that's a whole nother thing. All right, how are we doing? Oh, actual thumbs up so far, Zoomers. Would you like to vote? Where are your thumbs? We got wiggly thumbs, which I think means maybe okay, maybe not, I'm not sure. We have a standard error of measurement for our thumb scale. It wiggles across minutes of the class, right? How far off from okay are you at any given moment? All right, we got extra thumbs. So then where we're headed then is to talk about this E thing. So let me foreshadow that and then we'll call it a day. This line is a prediction. This is not the right answer, clearly. Like, look at this person up here. Why are they making bank with only a college degree? Are they an engineer or something? And then like people down here, like, this is my fellow psych majors. Woohoo! Or social workers or other people who do very important things in society and make no money, even though they have education. So why is it that this person with a college degree makes almost $70,000 and this person makes like nothing? I don't know. Neither does my model. So in talking about how good these numbers are, how helpful they are, we also want to pay attention to how much variability is there around this prediction. Because what's the least helpful predictor you can think of in terms of a line? If education absolutely had nothing to do with income, what would this line look like? Yeah, I'll take gestures. This is a gesture question. Flat. Right? If education had nothing to do with income, then it wouldn't matter. Where you are on X, you'd be at Y, the same place.
And then we should rethink.
And then you should rethink, yes. Yeah. So the tilt of the line, so to speak, speaks to the strength of the relationship, but you also have to look at how far wrong you are. So how much better did this line do at predicting Y than a flat line would? A flat line is what we would have had before we put this variable in here. The empty model, where we started with. If I didn't have income or education as part of the model, what was my predicted income for each person? The mean, 17. So how much better than just giving everybody 17 and calling a day did we do by putting X in here? That's what we get to talk about on Thursday. How's that for foreshadowing?
And that one means every individual, or the I means every individual?
Yeah, these are people. We're back to
Each
people.
person, yes.
Yep. But foreshadowing this, if I redid this study 100 times, do you think I'd get a slope of 1.82 every time? Nope.
For this, but ideally, you would. I mean, not 1.82, but somewhere around there, or it's garbage.
Ideally, yes. But in
Or
any
maybe that's what you want to show in the research that it is, like that it doesn't, like there's still reason to justify, like.
Well, it's still
something
worth doing.
that's not replicable.
Yeah, it's still worth doing, but in the same way that we wanted to know whether the mean is really 17 or how wiggly it is, we want to know, is this slope really 1.82 or how wiggly is it going to be? So guess what? The slope's going to have a standard error also. And the intercept's going to have a standard error also. Everything. Everything you get back is going to have some kind of, how wiggly is this expected to be, standard error that goes with it.
And the standard error we were talking about was in the sample.
Standard error is a estimated by a sample, but it's supposed to talk about the behavior of multiple samples sort of in the population that we don't have. Yep. Okay, question about homework. So homework you can do right now. Your first homework is homework 1. So homework 0 was just extra credit to test the system. Homework 1 you can do right now. There's absolutely nothing stopping you. You have a week to work on it. It's covering the very first lecture and a set of examples. So getting the mean, getting the variance, getting the frequencies, that's all it is. We have another 2 classes, I think, that I'm expecting to get through this unit, maybe 3. And then I'll have another homework that shows up for this one. So absolutely, you can do your homework. Speaking of next time, Thursday, we're being kicked out of this classroom. Comprehensive exams are happening in here instead, so we are being kicked out, which means we're back to Zoom for Thursday only. So I shall see you from my basement and your offices or your basements or wherever. All right, any other questions before we eject for today? Okay, then that's it. Thank you for coming. Thank you for the questions. Bye, everybody.